You move 1 light year every second, 6 trillion miles gone with each tick of your clock, and suddenly every distance you've ever heard in astronomy gets crushed into something you can actually feel. The entire solar system is gone in a blink. The Milky Way is a day-long sprint. The gap to Andromeda is a month-long commute. And the edge of the observable universe is only a few thousand of your years away. In this video, you're going to ride that impossible speed straight out of the solar system, across our galaxy, through clusters, along the cosmic web, all the way to the limits set by the Big Bang and dark energy, and see, step by brutal step, just how small, how late, and how boxed in our little patch of space really is. But before we continue, please subscribe to the channel to give your support. Let's continue. Start with one simple fix. A light year is a distance, not a time. It is the length of the path that light covers in 1 year, moving at about 186,000 miles per second, about 300,000 kilometers per second. You take that speed, multiply by all the seconds in a year, and you get around 6 trillion miles, roughly 10 trillion kilometers. So when a star is 4 light years away, that does not mean 4 years long. It means about 24 trillion miles, around 40 trillion kilometers of empty space between you and that star. So if a light year is just distance, what does 1 light year per second really mean for your speed? It means every second that passes on your clock, you cover about 6 trillion miles, 10 trillion kilometers. Light itself needs a full year to cover that stretch. You do it in 1 second. For normal human thinking, that is off the charts. But to see how extreme it is, you should compare it to speeds you already know. Think about the basic scale of our orbit. Earth is about 93 million miles from the Sun, about 150 million kilometers. Light covers that distance in a little more than 8 minutes. At 1 light year per second, you cross that Sun-Earth distance in far less than 1,000th of a second. You are through the whole inner orbit region before most people could even react. Now, compared to real spacecraft, New Horizons left Earth at about 36,000 miles per hour, about 58,000 kilometers per hour. The Parker Solar Probe has reached over 430,000 miles per hour, about 700,000 kilometers per hour. These are record-breaking speeds by engineering standards, but next to 1 light year per second, they might as well be parked. The distance you gain in a single second at this speed would take New Horizons tens of thousands of years to match. If you are that fast, you should ask how it scales when you stop thinking about planets and start thinking about the galaxy. The Milky Way's disk is roughly 100,000 light-years wide. Light needs 100,000 years to go from one side to the other. You, at 1 light year per second, would cross that span in about 100,000 seconds, a little over a day. What we call galactic scale turns into something you can cross in the time between one sunrise and the next. In those hours, you would move across the entire disk, from the outskirts, through the spiral arms, past the crowded center, and out the other side, all because each second is worth another full light year of distance. But distance in astronomy is never just about how far away something is right now. It's also about how long its light has been on the road. This is where look-back time comes in. When you look at a star 10 light years away, you see light that left it 10 years ago. A galaxy a billion light years away is seen as it was a billion years ago. The farther out you look, the earlier in the universe's history you are sampling. So when you think, I am at a distance of 1 billion light years, you're also saying, I am looking at light that has been traveling for 1 billion years. Distance and time are locked together in the way the universe reveals itself. That raises a sharp problem. In real physics, nothing with mass can reach the speed of light, let alone go beyond it. Special relativity says that as an object with mass speeds up, its energy requirement grows faster and faster, and as you approach the speed of light, the required energy shoots toward infinity. Hitting the speed of light would already need infinity energy, so going faster than that is simply not allowed. A real ship, a real probe, cannot cover a light year in a second, so this setup is not a design. It's a clean, controlled break from reality. You're turning off relativity for a moment and using this impossible speed as a tool to think clearly about distance and time, not as something you would actually try to build. But why keep using a speed that physics will never let you reach? Because at 1 light year per second, your mental bookkeeping becomes very simple. 1 second of your motion equals 1 year of light travel. 10 seconds is 10 years. A million seconds is a million years. When you hear this galaxy is 10 billion light years away, you can map that to that's 10 billion seconds of my travel, which is a bit more than 300 years. It gives you a direct link between the huge numbers astronomers quote and a clock you can feel, ticking in seconds. This is how that speed turns into a kind of time slider through the observable universe. Picture your position as a single number on a distance counter, increasing by 1 light year with each tick of a second. As that number climbs, the things around you are not just farther away in miles, they're tied to light that has been moving for longer and longer. Nearby galaxies around you correspond to hundreds of millions of years of look-back time. Very distant galaxies around you correspond to billions of years of look-back time. Push the counter far enough away, and you're in regions where the light started its trip when the universe was young, when galaxies were smaller, rougher, and forming stars at much higher rates than we see locally. There is a darker twist here. Even after you cheat the laws of physics and hand yourself this impossible speed, the scales you are about to deal with still barely fit into your mind. 1 second now equals a year of light travel. A few hours equals the crossing time of a galaxy. A few hundred years of your travel equals a look-back time that reaches almost to the beginning of galaxies themselves. If that is what this speed does before you have even left your home system properly, what happens in the very first second when you aim this impossible drive outward and fire, right from the middle of the solar system? How fast do things disappear when you move at 1 light year per second right from the middle of the solar system? The answer is the entire region you think of as home is gone almost before you can react. Start with Earth's orbit. Earth orbits the Sun at about 93 million miles away, about 150 million kilometers. Light from the Sun takes a bit over 8 minutes to reach Earth. Your speed is 6 trillion miles per second, about 10 trillion kilometers per second. So how long do you spend crossing that 93 million mile gap? You take 93 million, divide by 6 trillion, and you get a time of around 15 millionths of a second. That is less than 100,000th of a second. By the time your brain even processes the fact that you hit go, you have already gone from the orbit of Mercury through Earth's orbit out past Mars. The entire inner solar system zone that we talk about in school is compressed into a tiny slice of your very first blink. If the inner planets vanish in a microfraction of a second, what happens to the big outer planets that everyone thinks of as far away? Look at the gas giants. Jupiter orbits at about 480 million miles from the Sun, about 778 million kilometers. Saturn is around 880 million miles out, about 1.4 billion kilometers. Uranus is about 1.8 billion miles away, around 2.9 billion kilometers, and Neptune is near 2.8 billion miles, around 4.5 billion kilometers. Even the farthest of those, Neptune, is still only a tiny fraction of a light year. 2.8 billion divided by 6 trillion gives you less than 5/10,000ths of a second. That means from the Sun to Neptune's orbit, the whole main planetary zone, inner planets plus gas giants, is gone in under half of a millisecond. Every world you have ever heard about, every place any probe has ever visited, falls behind almost instantly. The solar system that took billions of years to build is a small numerical rounding error in your very first second. So if the main planetary zone is that small on your speed scale, what about the so-called outer solar system, the part full of dwarf planets and icy leftovers? The Kuiper Belt extends from just beyond Neptune out to about 4.6 billion miles from the Sun, roughly 7.4 billion kilometers. Pluto lives in this region. This belt is thick with icy bodies, each tens to hundreds of miles across, leftovers from planet formation. On human terms, 4.6 billion miles is shocking. It's about 50 times the Earth-Sun distance. For light, it's a several hours of flight. For you, at 1 light year per second, it's still well under 1,000th of a second. You cross the entire Kuiper Belt in about 8/10,000th of a second. You do not thread your way between objects. You just cross a huge empty volume with rare, scattered ice balls that you barely have time to register before they are behind you. If even Pluto's neighborhood goes by that quickly, what counts as leaving the solar system now? Beyond the Kuiper Belt, there is the scattered disk, a population of icy bodies on stretched, tilted orbits that can go hundreds of times farther than the Sun than Earth does. Past that, somewhere around 2,000 to maybe 5,000 times the Earth-Sun distance, you hit what astronomers call the inner edge of the Oort cloud. That's a spherical reservoir of icy bodies, likely trillions of them, that can stretch out to around 100,000 times the Earth-Sun distance, which is roughly 1.5 to 2 light years. On normal scales, that's the true edge of the solar system's comet supply. On your scale, 1 light year per second, the entire distance from the start of the inner Oort cloud to the far outer edge is crossed in about 1 to 2 seconds. The region that holds the long-period comets, the ones that drop into the inner solar system once every millions of years, is just a thin shell in your first couple of heartbeats. So how does this compare to the fastest real machines we have? Take Voyager 1. It launched in 1977, flew past Jupiter and Saturn, and is now far beyond the planets, moving at about 38,000 miles per hour, around 61,000 kilometers per hour. After almost 5 decades, it's tens of billions of miles from the Sun, a little over 100 times the Earth-Sun distance. That's only a few thousandths of a light year. At your speed, you cross that entire span in a few thousandths of a second. Everything Voyager 1 has done, all the ground it has covered in half a human lifetime, is a flicker along your path. Voyager 2, on a different route, is a bit closer in, also moving tens of thousands of miles per hour. New Horizons, the probe that flew by Pluto, left Earth at about 36,000 miles per hour, about 58,000 kilometers per hour. If one of these probes tried to travel a full light year at its current speed, it would need on the order of 20,000 years. You do that same light year in 1 second. They're still trapped in the first thin shell around the Sun, while you are already far beyond the entire comet cloud region before you finish counting 1, 2. So you clear the Oort cloud and leave all our probes behind almost instantly, but are you really free from the solar system at that point? Or does gravity still have a claim on you? The Sun's gravity doesn't suddenly stop at some sharp wall. Its influence fades with distance, but technically it reaches out forever. The practical edge of the Sun's control is set by the tug-of-war between the Sun and the rest of the Milky Way. Astronomers call this the Sun's Hill sphere, a region maybe a few light years across, inside which objects can stay loosely bound to the Sun over long times. The Oort cloud likely occupies the inner part of that region. In a slow, fragile setting, small icy bodies out there still belong to the Sun in a gravitational sense, looping around it over tens of millions of years. But now compare that slow, fragile binding to your speed. Escape velocity from the solar system at Earth distance is a few tens of miles per second. Your speed is not tens of miles per second, it's trillions of miles per second. You are so far above the escape speed that the Sun's gravity barely bends your path. Yes, in a mathematical sense, the Sun's gravity still extends out to where you are, but for your trajectory, the solar system is effectively gone the moment you switch this drive on. Any chance of swinging back, turning around, orbiting again would require such huge changes in your speed that it's not worth even talking about. On your scale, being gravitationally bound and being effectively lost forever are totally different things, and you left the effectively lost forever stage behind in your very first second. So here's the key point you have just learned. Before you even hit the 2-second mark, every structure you grew up with, every planet, every dwarf planet, every famous probe, plus the entire comet reservoir that feeds long-period comets into the inner system, is compressed into the tiniest first step of this journey. At 1 light year per second, the solar system is not a place you travel through. It is just the starting coordinate you leap away from. If your home system collapses into a tiny blip on your personal distance scale that fast, what happens when you keep going and the first thing in front of you now is not a planet or a comet belt, but the empty space between stars in the Sun's local neighborhood? You have already thrown the whole solar system behind you in under 2 seconds. So what actually fills the next 10 seconds, the next dozen light years of your trip? First, you need to know where the Sun sits on a larger scale. The Sun is inside something called the local bubble. a cavity in the Milky Way's gas and dust that is roughly 1,000 light-years wide. This bubble is not empty, but it has gas that is much thinner than average, heated to millions of degrees by old stellar explosions. Instead of cold, dense clouds, you are moving through extremely thin, hot plasma. At 1 light-year per second, 1,000 light-years is about 1,000 seconds, a bit over 17 minutes. So for your first minutes, and definitely for your first dozen seconds, you are still deep inside this cavity carved out by past violence in our part of the galaxy. You are not leaving the local bubble quickly, even though you just left the solar system almost instantly. If you are inside a huge, low-density bubble, does that mean there are no stars nearby, just empty volume? Not at all. Even inside this cavity, the sun has neighbors, and at your speed, you cross the distance to them almost immediately. The closest star to the sun is Proxima Centauri, about 4.24 light-years away. In normal language, that means the light you see from Proxima tonight left that star a little over 4 years ago. For you, at 1 light-year per second, that is a trip of about 4.24 seconds. You count 1, 2, 3, 4, and you have already passed the distance light takes more than 4 years to cover. Proxima itself is a small red dwarf, cooler and dimmer than the sun, with at least one planet in its habitable zone. A bit farther out, at around 4.37 light-years, is the Alpha Centauri system as a whole, the brighter pair of sun-like stars plus Proxima in a wider orbit. In everyday astronomy, this is our next-door system. In your frame, you rush past the entire region they occupy in a fraction of the time it takes to read this sentence. Are those few stars isolated points in an otherwise empty region? When you look at real catalogs of nearby stars and brown dwarfs, the story changes. Within 10 light-years of the sun, astronomers count more than a dozen star systems, most of them small red dwarfs that are too faint to see with the naked eye. On top of that, there are brown dwarfs, objects too small to sustain normal hydrogen fusion, but too big to be called planets. They glow mostly in infrared, and many were only found in the last couple of decades. As surveys have improved, the list of nearby objects keeps growing. Space between stars is large, but it is not wide-open emptiness. Typical separations of a few light-years mean that inside a radius of, say, 12 light-years, you are already inside a loose, three-dimensional neighborhood of a few dozen stellar and substellar bodies. At your speed, you cross that whole local volume in 12 seconds, but on a map, it's a crowded little bubble of systems orbiting the galaxy together. If there are stars and brown dwarfs all around, packed into these dozens of light-years, why do astronomers still call this region a vacuum? The answer is in the gas and dust between those stars. The interstellar medium here has a density of only a few atoms per cubic centimeter, sometimes even less. Compare that to air at sea level on Earth, which has something like 10 billion molecules in the same volume. You would need to stack up a huge number of cubic centimeters of interstellar space to match the mass of the air inside a single human breath. So even inside the local bubble, which is made of slightly hotter, thinner gas than its surroundings, everything is so rarefied that you can move dozens of light years and, on average, hit almost nothing. Your ship's instruments would register a constant trickle of particles, but not much more. The big structures here are stars, brown dwarfs, and very diffuse clouds, all separated by volumes that are imaginably thinner than any vacuum you can create in a lab. If the gas is that thin, how did a 1,000 light-year wide bubble appear in the first place? Something had to push material out of the way. That something is a series of supernova explosions that went off in this part of the galaxy over the last 10 to 20 million years. Massive stars lived fast and died violently, blowing out shells of gas that expanded and overlapped, carving out this cavity. As you rush outward, you would cross regions where that past activity is still visible. There are supernova remnants, shells or filaments of slightly denser gas, expanding shock fronts, and arcs of dust where the blast ran into cooler material. Astronomers map these fossils using X-ray observations, ultraviolet data, and 3D dust maps built from how starlight is dimmed and reddened along different lines of sight. For your eyes, looking out of a window, they wouldn't show up as sharp walls, more as subtle changes in background glow and star counts. But in terms of physics, you are moving through the scars of old explosions that shape the entire local environment the sun travels through. All of this is happening while your own clock is burning through time at a ridiculous rate compared to the light around you. Remember what your speed means. 1 light year of distance per second along your path. 1 second on your watch equals 1 year of light travel. So in 12 seconds, you have covered 12 light years, and you have passed the distance from which light would have needed 12 years to reach the sun. In half a minute, 30 seconds, you are 30 light years out, ahead of light that will take 3 decades to reach. In 1 minute, you are 60 light years away. In 1 hour, you are 3,600 light years from where you started, still inside the broad local bubble, but now deep into parts of the galaxy the sun won't pass through for tens of millions of years on its actual orbit. That's the real weight of this thought experiment in your first 12 light years. Your sense of time and distance is getting ripped apart. Things that are only a few light years away, like Proxima Centauri, go by in a handful of seconds. The whole local neighborhood of stars and brown dwarfs, the thin gas of the local bubble, the shells of ancient supernova, all of that is compressed into the early part of a single minute on your clock. If seconds now correspond to years of photon flight and minutes correspond to thousands of years of it, what happens when you stop thinking in tens of light years and start covering tens of thousands, slicing straight across the Milky Way's disk itself? How long does it actually take you to cross a whole galaxy at 1 light year per second, and what do you see while you're doing it? You are not just drifting through a star field now, you are cutting through the main disk of the Milky Way itself. Start with the basic size. The Milky Way's disk is about 100,000 light years across and roughly 1,000 light years thick. At your speed, 1 light year per second, the thickness of the disk is only about 1,000 seconds, a bit over 17 minutes. Crossing the entire diameter, side to side, is about 100,000 seconds, just a bit over 27 hours. So in roughly a day, you can go from one edge of the disk through the central regions and out the other side, while light would need 100,000 years to do the same. Right now, you start near the sun's position in that disk. The sun is not at the center. It sits around 26 to 28,000 light years from the core, in the outer half of the disk. At 1 light year per second, that distance to the center is a trip of around 7 to 8 hours. So if you point yourself straight inward, your clock runs for less than a normal workday before you pass the densest, most crowded parts of the galaxy and keep going. The entire structure we live in, the thing we call our galaxy, is getting compressed into a rough, day-long sprint. The disk is not just a flat, boring plate of stars. It has spiral structure, and you live in one of those features. The sun is in a small spiral segment, often called the Orion arm or the Orion spur, between two larger arms, the Sagittarius arm closer in and the Perseus arm farther out. At your speed, those arms are like broad, curved bands of higher star density and gas that you slice through in minutes. Move inward, and you cross the Sagittarius arm region on the scale of tens of minutes. Move outward, and the Perseus arm comes and goes just as quickly. The big, grand design pattern that takes the galaxy hundreds of millions of years to rotate, you experience as a series of overdense regions flashing by in the span of a commute. All the way along this path, the star count is enormous. Astronomers estimate the Milky Way holds somewhere between about 100 billion and 400 billion stars. Why is that range so wide? Because most stars are small, dim red dwarfs, very hard to see over large distances, especially through dust. You only see the bright tip of the iceberg directly. To get total numbers, astronomers have to combine star counts in well-measured regions, models of how many low-mass stars are hidden, and overall mass estimates from how the galaxy rotates. Uncertainties in how many faint stars there are and how much of the mass is normal matter versus dark matter turn into a factor of a few in the total star count. So, as you cross the disk, you are passing hundreds of billions of suns, but the exact number is still not pinned down to better than a factor of a few. Those stars are not just floating alone. Mixed into the disk, you plow through giant molecular clouds, the real engines of star formation. These are cold, dense clouds of hydrogen molecules, plus dust and other molecules like carbon monoxide that can be tens to hundreds of light years across and contain the mass of 1,000,000 or more suns. Their internal temperatures are only a few tens of degrees above absolute zero. Gravity slowly pulls parts of them together, making clumps that collapse into new stars and planetary systems. At normal speeds, these clouds are long-lived structures. At your speed, a 100 light-year wide cloud is gone in about 100 seconds. You cross the places where stars like the sun are being born in a couple of minutes, and then they are behind you, replaced by new clouds, new pockets of gas, new forming clusters. The closer you get to the center, the more the scene changes. Star density rises. The disk thickens into a bulge, a more three-dimensional swarm of older stars, mixed with dust lanes and gas streams. At the very heart, a few tens of thousands of light years in from where you started, sits the central bar, a stretched structure of stars that runs through the inner galaxy. Bars help funnel gas toward the center, feeding both star formation and the supermassive black hole called Sagittarius A that sits in the middle. Sagittarius A has a mass of about 4 million suns. Stars orbit within a light day of it, whipping around at thousands of miles per second. At your speed, you cross the entire central few thousand light years, bar plus bulge, in less than an hour. Even the region dominated by a 4 million solar mass black hole is just another dense patch that your insane velocity carries you straight past. You might expect such a key feature as the disk and its rotation to be mapped in perfect detail by now, but our view from inside makes that hard. This is where real surveys come in. The Gaia mission is measuring positions, distances, and motions for well over 1 billion stars, giving a detailed three-dimensional map of the local and mid-range parts of the disk, and mapping how stars move along their orbits. Radio surveys of neutral hydrogen using the 21-centimeter line trace gas across the disk, even through dust that blocks visible light. Carbon monoxide maps trace molecular clouds, showing where star-forming regions pile up along the arms. By combining all this, astronomers derive the galaxy's rotation curve, the way orbital speed changes with radius. That curve stays roughly flat far out in the disk, which tells us there is a large amount of invisible dark matter holding the system together. As you sprint across the disk, all that careful work collapses into a simple fact you can feel. This flat structure is huge in human terms, but thin in galactic terms. You clicked past the first few thousand light years from the sun in less than an hour. You crossed the densest inner regions in another hour or so. You finished the last tens of thousands of light years toward the opposite edge in the time it takes to sleep and wake up again. Hundreds of billions of stars, spiral arms, bars, bulges, and the central black hole all got compressed into under 2 days of travel on your clock. So now you have a problem. If the Milky Way's entire disk turns into something you can cross this fast, what does it look like when you stop flying inside the plane and instead blast straight up, out of the disk, into the much larger, more diffuse structures above and below it, where the real halo and dark matter live? How long does it really take you to leave the Milky Way's main plane and see the whole thing from above? At 1 light year per second, the answer is not long at all. The disk is about 1,000 light years thick. You are already inside that layer, near the midplane where the sun orbits. Aim straight up, away from the disk, and 1,000 seconds means 1,000 seconds, a bit over 17 minutes. That's enough to pop out of the main star layer. In the time someone on Earth watches a short show, you've climbed out of the crowded band and reached the height where the Milky Way looks thin in the distant direction, a narrow slab of stars and gas below you, roughly 100,000 light years across, but only 1,000 light years thick. What's waiting for you once the bright disk is below you? Outside the disk is the stellar halo, a much more diffuse population of stars that surrounds the galaxy in a roughly spherical cloud. These halo stars are usually old and metal poor, which means that compared to the Sun, they have much less of the heavier elements like carbon, oxygen, and iron. Their chemical fingerprints say they formed early, before many rounds of star birth and death enriched the gas. At your speed, you cross regions of the halo where individual stars are separated by hundreds or thousands of light years. But because you're traveling 1 light year every second, those gaps last minutes on your clock, not ages. The halo is not just random, lonely stars. One of the key features you would see from this vantage point are long, thin structures called tidal streams. These are the remains of small galaxies that got too close to the Milky Way and were torn apart by gravity. Their stars were stretched out along their orbits, forming huge arcs that can wrap partway around the galaxy. The Sagittarius stream is a clear example, coming from the Sagittarius dwarf galaxy that is currently being shredded. At normal speeds, these streams are static patterns in the sky. For you, they are lanes of slightly higher star density that you cross in hundreds or thousands of seconds as you move through the halo. Each stream records a past act of galactic cannibalism, and you could cross several of them in the time it takes you to cross a few tens of thousands of light years. Along with these streams, you run into compact, dense systems called globular clusters. How dense can a star cluster really get? A typical globular cluster packs hundreds of thousands of stars into a sphere only about 100 light years wide. Compared to the solar neighborhood, where the nearest star is more than 4 light years away, the cores of these clusters are crowded with stars only fractions of a light year apart. Many globulars orbit far above and below the disk, on paths that carry them through the galaxy's outskirts and back through the inner regions. At 1 light year per second, you go from one side of a globular cluster to the other in about 100 seconds. You cross an object that contains the mass of up to 1,000,000 suns, full of some of the oldest stars in the galaxy, in less time than it takes to make a cup of coffee. All of that, the halo stars, the tidal streams, the globular clusters, is the visible part. Underneath it sits something far larger that you cannot see directly, the dark matter halo. The bright disk is about 100,000 light years across. The dark matter halo around it extends out to a few 100,000 light years, maybe up to 300,000 or more, and it holds most of the Milky Way's mass. This invisible halo is what keeps the outer parts of the galaxy rotating as fast as they do, instead of slowing down with distance from the center. On your scale, crossing the region where the disk dominates takes about a day, but plunging far into the dark matter halo takes several days of travel at 1 light year per second. Even then, you are still inside the galaxy's overall gravitational envelope. If dark matter is invisible, how do you even know you are moving through a bigger, heavier structure out here? You do not see dark matter directly, but you see its effects. The rotation curve of the Milky Way stays roughly flat with radius, which means outer stars orbit faster than they should if only visible matter were present. The motions of halo stars, globular clusters, and dwarf galaxies show that there is extra mass pulling on them from all directions. Gravitational lensing, where mass bends the path of light from background objects, also reveals dark matter in other galaxies and clusters. Taken together, those measurements support the idea that our galaxy is sitting in its own large halo. You are flying through a region where most of the mass is in a form that does not emit light, but its gravity has shaped everything you already passed through. How do astronomers actually map all this three-dimensional structure when they are stuck down in the plane of the disk, and you have this clean top-down view? They use a mix of star counts, distance measurements, and velocities. Surveys like Gaia measure positions and motions for huge numbers of stars, including halo stars and members of tidal streams. Deep imaging finds globular clusters and faint dwarf galaxies. Spectroscopy reveals the chemical compositions of stars, letting astronomers separate old, metal-poor halo stars from younger disk stars. For dark matter, they lean on dynamics and on gravitational lensing, especially in other systems where lensing can be measured clearly. Put together, these methods build a three-dimensional model you are now blasting through in minutes and hours. So now, look at your situation. In less than half an hour, you climbed out of the disk. In a few more hours, you crossed through the inner halo, past globular clusters and tidal streams, into regions where dark matter outweighs visible matter by several times. In a couple of days at this speed, you can move hundreds of thousands of light years from where you started, far beyond the Milky Way's bright disk, and still be under the pull of its dark halo. If it only takes you days to clear the main body of your own galaxy, what happens when you keep going until the Milky Way is just one member of a larger group, and the next thing in front of you is another giant galaxy, Andromeda, a couple of million light years away? You left the Milky Way's halo behind in a couple of days of your own time, so the next question is simple. How big is your actual neighborhood, the one where our galaxy is not alone? Your home environment is called the local group. At the top level, it's dominated by three big galaxies, the Milky Way, Andromeda, and Triangulum. The Milky Way is your starting point, a large spiral with a disk around 100,000 light-years wide. Andromeda, also a spiral, is a bit bigger and more massive. Triangulum is smaller, but still a serious galaxy, not a dwarf. These three sit inside a loose, gravitationally bound cluster of a few dozen smaller galaxies, all orbiting the shared center of mass. At your speed of 1 light-year per second, this whole structure is not an abstract cloud of names. It becomes a set of concrete travel times. Look at Andromeda first, because that's the main other player here. It's about 2.5 million light-years away from the Milky Way. For light, that distance means a travel time of about 2.5 million seconds. For you, at 1 light-year per second, it's around 2.5 million seconds. That's roughly 29 days. So, on your clock, you could leave the Milky Way, aim straight at Andromeda, and reach the distance of its center in under a month. You go from one major spiral galaxy to another in the time it takes someone on Earth to get through a long vacation or a work project, while the light connecting them has been flying since long before our species existed. Triangulum, the third large member, sits a bit farther out, roughly 3 million light-years away. That has just a few more days at your speed. It's smaller and less massive than the Milky Way or Andromeda, but still contains tens of billions of stars. In normal astronomy, these three big galaxies define the local group's backbone. In your frame, they're a set of waypoints separated by tens of days, not millions of years. You can run a route that goes Milky Way to Andromeda to Triangulum and back within a span of months, crossing distances that light itself takes millions of years to cover once. The local group is not just those three heavyweights. There are dozens of dwarf galaxies bound to them. Around the Milky Way, you have the large and small Magellanic Clouds, irregular dwarf galaxies at about 160,000 and 200,000 light-years away. So, at your speed, well under 3 minutes of travel each. They're actively forming stars. They have their own gas and dark matter, and they're being pulled and distorted by the Milky Way's gravity. There are fainter dwarfs like Draco, Ursa Minor, Sculpture, and many ultra-faint dwarfs, each containing only tens of thousands of stars. Around Andromeda, there's another swarm of dwarfs with names like M32 and NGC 205. As surveys have improved, especially with large digital sky maps, the list of known dwarfs has exploded. Many of these galaxies are so low in brightness that they were missed until recently. At your speed, each one is a tiny detour, a few seconds to a few minutes away, but they're real galaxies with their own stars, their own dark matter halos, and their own orbital paths around the big spirals. All of these orbits hint at the local group's future. Andromeda is not static on the sky. It has a proper motion, a sideways velocity, and a radial velocity, a motion towards or away from us. The key fact is it's moving towards the Milky Way at hundreds of kilometers per second, which is hundreds of thousands of miles per hour. For a long time, the sideways component was uncertain, and that uncertainty affected the predicted future. Detailed measurements, especially with the Hubble Space Telescope and now Gaia, suggest that the chance of a direct head-on collision versus a near miss is roughly balanced, about 50-50, over the next several billion years, and some newer work has shifted the timing and details compared to older estimates. Either way, we're looking at a likely major interaction on the order of several to 10 billion years from now. On those timescales, the two big halos, the Milky Way and Andromeda, will pull each other in. Their disks will distort, long tidal tails will form, and after a few passes, they will probably merge into a single, more spherical galaxy. Triangulum and many dwarfs will get caught up in this too. On your scale, the collision timescales are the only thing you cannot compress. You can cross the distance between the galaxies in weeks, but you cannot speed up the billions of years of orbital dance that lead to a merger. That is set by gravity, not by your engine. So even though you can jump from one galaxy to another almost casually, the underlying structure of the local group is still evolving on huge timescales that you simply cannot shortcut. Now look again at your travel times. The Milky Way's disk took you a bit more than a day to cross. Climbing out into the halo and pushing a few 100,000 light-years away took you a few days. Going all the way to Andromeda's center is under a month. Triangulum is a few more days. If you define the local group as the region where all these galaxies and dwarfs are gravitationally bound together, you are talking about a volume a few million light-years across. At 1 light-year per second, a million light-years is about 12 days on your clock. 10 million light-years is a few months, and out here, those are the kinds of gaps you're dealing with. You're still crossing galaxies now and then, but there are long stretches in between where the main thing around you is dark, expanding space. So what is the next real target ahead of you? The nearest large galaxy cluster is the Virgo Cluster, sitting about 50 to 55 million light-years away. For light, that's 50 to 55 million years of travel. For you, that distance is 50 to 55 million seconds, which is on the order of a year and a half to almost 2 years. That is still a lot of time for you, but think about what that means. A structure that light only reaches after tens of millions of years is something you can run down in under a couple of Earth years. The Virgo Cluster is not just a single galaxy. It holds hundreds to thousands of galaxies packed into a region a few million light-years across, and you're rushing straight toward that higher density island in a mostly thin sea. You are not drifting through this space at random. On large scales, matter is arranged in filaments, long threads of galaxies and groups that connect clusters like Virgo. The local group sits on one of these filaments, sometimes called the local filament, that stretches out and links our small group to Virgo and other structures. As you move forward, if you could pause and rotate your view, you would see galaxies not evenly spread out, but gathered along these thread-like patterns. Some routes through this space are relatively rich, lined with small groups and mid-sized galaxies, while large voids off to the side are nearly empty. Your path towards Virgo follows one of these cosmic highways, where gravity has been slowly pulling matter together for billions of years. How do we know we're actually moving along a preferred direction like this and not just sitting still while the universe expands around us? This is where the idea of peculiar velocity comes in. Hubble's law says that on large scales, galaxies recede from each other because space is expanding, and the farther away they are, the faster they seem to move away. But on top of that smooth expansion, each galaxy or group can have its own extra motion, its peculiar velocity, caused by gravity pulling it toward over-dense regions. When astronomers look at the local group's motion relative to the cosmic microwave background, they see that we have a significant velocity toward the general direction of Virgo and beyond. This flow, often called the Virgo-centric flow, is the sign that the mass in Virgo and the surrounding supercluster environment is tugging on us. You and every galaxy around you are slowly sliding downhill in the gravitational landscape, even while the universe as a whole expands. You are cutting across this landscape at 1 light-year per second, but the actual gravitational drift is slow. Typical velocities relative to the expansion are a few hundred miles per second, maybe 1,000 or so in extreme cases. At those speeds, crossing even a few million light-years takes many billions of years. That's why from the point of view of any normal galaxy, the journey from a small group like the local group toward the dense heart of a cluster like Virgo is painfully slow, something that can span the entire age of the universe. On your clock, you don't wait for this, you overtake it. You can move through the space that those flows will gradually fill long before gravity fully rearranges the map. To talk about flows and attraction, you first need to know precise distances, not just rough guesses. That's where distance indicators come in. Cepheid variable stars are one of the most important. These stars pulse in brightness in a regular pattern, and there's a direct link between the period of that pulsation and their true luminosity. By measuring how fast they blink and how bright they look, astronomers can calculate how far away they are. Type 1a supernovae are another key tool. These are exploding white dwarfs that reach nearly the same intrinsic brightness each time. Because their true power is well understood, they act as standard candles on much larger scales. By using Cepheids to anchor distances in nearby galaxies and then using Type 1a supernovae to jump out farther, astronomers build a distance ladder that stretches all the way from the local group into clusters like Virgo and beyond. Once you have reliable distances, you can compare how fast each galaxy is moving away or sometimes toward us based on its redshift or blueshift with how fast it should be moving just from cosmic expansion alone. The difference, the peculiar velocity, tells you which way gravity is pulling it. When you look at enough galaxies between the local group and Virgo, you see a pattern, a component of their motion that points toward the cluster. This is how you know that the Virgo cluster is not just another object in the background. It's part of a larger gravitational structure that is influencing our motion even now. Now compare your timescale to all of this. In 1 minute, at 1 light year per second, you move 60 light years. In an hour, you move 3,600 light years. In a year, you move over 30 million light years. Over the same span, a typical galaxy might drift a tiny fraction of that distance under the pull of structures like Virgo and the surrounding supercluster, because its speed is limited to a few hundred miles per second. The paths that galaxies trace out slowly over tens or hundreds of millions of years, you cross in what feels like a straight line at almost ridiculous speed. You are essentially stepping over the very process that shaped these filaments and flows in the first place. So here is where the tension really starts to climb. You are moving from the quiet outskirts into the sphere of influence of the nearest big cluster, racing along a filament that has been forming since near the beginning of cosmic time. The distances between groups have grown with the expansion of the universe, gravity has fought back to pull clusters together, and all of that long, slow battle is frozen into the pattern you're rushing through in months. If that is what happens just on the way in, what happens when you finally reach the cluster itself, where hundreds or thousands of galaxies, hot gas, and dark matter are jammed together in a much smaller region, and every interaction is more violent and more extreme? How different does the universe look when you stop coasting through loose groups and drive straight into a real galaxy cluster? This is where everything you have seen so far starts to feel small. The Virgo cluster packs hundreds to maybe a couple of thousand galaxies into a region only a few million light years across. Compared to the local group, which spreads just a few big galaxies over a few million light years, Virgo is crowded. The core region, the densest part, is maybe 2 to 3 million light years wide. Light takes a few million years to cross that. You, at 1 light year per second, cross it in a few million seconds, so on the order of a month. That means you can enter the near side of Virgo, cut through its core, and exit the far side in about as much time as you just spent getting here from the local group. But the density jump is huge. Instead of seeing one big galaxy every few million light years, you see them everywhere, piled up, overlapping on the sky, orbiting in a deep shared gravitational well. If there are that many galaxies in such a small space, what is actually between them? The answer is not vacuum. It is hot intracluster plasma. The space between Virgo's galaxies is filled with gas heated to tens of millions of degrees. At those temperatures, the atoms are ripped into nuclei and electrons, and the gas glows strongly in X-rays. X-ray telescopes like Chandra and XMM Newton see Virgo not as a handful of bright spots, but as a huge extended cloud of X-ray emission centered on the cluster core. This intracluster medium actually holds more normal matter than all the stars in all the galaxies combined. You are flying through a very thin, extremely hot gas that fills the cluster's volume, and every galaxy moving inside it has to push through this stuff at thousands of miles per second. So which galaxies stand out in this environment? One of the key players in Virgo is M87, a giant elliptical galaxy near the cluster center. It's huge, much larger and more massive than the Milky Way, and it hosts a supermassive black hole with a mass of several billion suns. That's the black hole whose shadow was imaged by the Event Horizon Telescope. M87 also launches a relativistic jet, a narrow stream of particles moving at speeds close to the speed of light, shooting out thousands of light years into space. At your speed, you cross the length of that jet in a few thousand seconds, under an hour. But the physics behind it is extreme, involving magnetic fields, accretion disks of hot gas, and a twisting of space-time near the black hole. In a cluster like Virgo, central giants like M87 act as anchors, sitting at the bottom of the gravitational potential well and collecting gas and smaller galaxies over billions of years. Now think about what happens to normal galaxies that are not sitting at the very center, but orbiting through this hot plasma. As they move at high speed through the intra-cluster medium, they experience something like a headwind. Gas in the galaxy, especially in its outer disk, feels this pressure and can get stripped away. This process is called ram pressure stripping. Spiral galaxies that fall into Virgo often show one-sided tails of gas trailing behind them, with their gas disks truncated and their star formation quenched. You can think of them as cars driving through a storm, losing their outer layers in the flow. At your scale, you would see some spirals with neat, symmetrical disks, and others with gas flowing away in long, faint streams, clear signs that the cluster environment is actively changing them. This is not just theory. Recent observations around Virgo show dramatic features, like hydrogen bridges about 185,000 light-years long connecting galaxies, and gas tails stretching more than 1.6 million light-years. These structures are far bigger than any single galaxy. They form when galaxies interact with each other and with the cluster medium, pulling gas out and leaving behind enormous filaments and plumes. At your speed, a 185,000 light-year bridge takes about that many seconds, a couple of days. A 1.6 million light-year gas tail takes 19 days. So even on your extreme scale, these are not tiny details. They are multi-day crossings, signs that the cluster is constantly rearranging its gas and galaxies, building up larger structures from smaller pieces, and slowly starving galaxies of the fuel they need for new stars. All this visible matter, the galaxies and the hot plasma, is only part of the story. The real mass of Virgo is dominated by dark matter, and you can see that indirectly through dynamics and lensing. First, look at galaxy speeds. The galaxies in Virgo orbit the cluster center at hundreds to over 1,000 miles per second. If you add up the mass of all the visible stars and gas, there's not enough gravity to hold them in. The cluster would fly apart. The fact that it holds together tells you there must be much more mass than you can see. That unseen mass is mapped as a deep gravitational well, filled with dark matter. Second, gravitational lensing shows the same thing. Light from more distant background galaxies gets bent and distorted as it passes through Virgo's mass distribution. By measuring how those shapes are stretched and sheared, astronomers reconstruct the cluster's mass distribution. The lensing maps line up with but extend far beyond the regions traced by stars and gas, confirming that a huge halo of dark matter surrounds and permeates the cluster. You are cutting straight through that halo, through hot plasma, past giant ellipticals, past spirals being stripped bare, through gas bridges and million light-year tails. In a few weeks of your time, you've crossed a region that galaxies take billions of years to orbit through. The cluster is stable on your timescale, but everything in it is actually in motion, slowly sinking deeper into the potential well, gradually losing gas, merging, and transforming. You are moving so fast that you only see a frozen snapshot of that process, but the evidence of long-term violence is everywhere. So here is where the new pressure point. You started with one star and one planetary system. Now you've blown past the whole galaxy and past an entire massive cluster packed with hundreds to thousands of galaxies in a human-scale amount of time. If a cluster like Virgo can be crossed in weeks, what happens when you keep going, when you pull back far enough that even massive clusters stop being the main structure, and what really matters is the pattern of filaments, walls, and huge empty voids on scales of tens and hundreds of millions of light years? How do you make a whole galaxy cluster like Virgo feel small? You step back until it's just one knot in a much larger pattern, and that pattern is the cosmic web. Now you're thinking in tens and hundreds of millions of light years. At 1 light year per second, 10 million light years is a bit over 4 months. 100 million light years is a little over 3 years. Those are the scales where the web-like arrangement of matter shows up. Galaxies are not scattered randomly. They sit in long chains, broad sheets, and big junctions, with huge gaps in between. Clusters like Virgo are just the densest intersections where many of these chains or filaments meet. So what are these filaments actually like? A typical filament can be tens of millions of light years long, sometimes more, and a few million light years thick. They bind clusters together into larger supercluster structures. Along each filament, you see groups and clusters of galaxies, like beads on a wire. Between them, the density drops, but never to zero. There's dark matter, there's thin gas, and there are smaller galaxies scattered along the length. At your speed, crossing a 10 million light-year filament from one side to the other is 10 million seconds, a few months. Running along its length for 50 million light years is on the order of a year and a half. The key point is these are continuous structures, not isolated islands. You are traveling through long, connected ridges of matter that channel the flow of galaxies and gas over cosmic time. If there are dense filaments, there must also be the opposite, places where almost nothing lives. Those are the voids. A large cosmic void can be tens of millions of light years across, sometimes over 100 million. Inside, the number of galaxies drops dramatically, maybe a few dim ones scattered through a volume that, at cluster densities, would hold thousands. If you aim yourself into one of these regions, you can travel for millions of light years, months, or years on your clock, and see only the occasional faint galaxy off to the side. The average density of matter is still there. Dark matter still fills space, but in terms of bright galaxies, it looks almost empty. You have gone from the crowded core of Virgo to stretches where the main thing you see is the backdrop of more distant structures, wrapped around the void like a loose shell. Here's one twist that shows how complex these structures really are. Some recent work points to whole cosmic filaments that are not just static bridges, but actually rotating. These filaments can span something like 50 million light years and contain hundreds of galaxies. Yet there are signals that material is moving around the filament's long axis, slowly over billions of years. It's not rotation like a solid rod, more a pattern where galaxies on one side tend to move in one direction along the line of sight, and galaxies on the other side move in the opposite sense, hinting at a global spin. The speeds involved are small compared to the speed of light, but the size makes it dramatic. You are moving along or across structures that may be twisting as they feed matter into clusters at their ends. How do we know about any of this when you don't have a God's eye view in real life? Large galaxy redshift surveys do the heavy lifting. Projects like the Sloan Digital Sky Survey and DESI measure positions and redshifts for millions of galaxies. The sky position gives you two angles. The redshift, which tells you how much the light is stretched by cosmic expansion, acts as a rough distance indicator. Put those together and you get a three-dimensional map. When you plot millions of galaxies in 3D, the cosmic web pops out automatically. You see filaments, walls, and voids, not because someone drew them in, but because that is how the points are actually arranged. DESI and similar programs are pushing this to greater depths and finer detail, giving better statistics on how big these structures are, how common they are, and how they grow over time. On top of that, you can compare the galaxy maps to simulations of structure formation in a universe with dark matter and dark energy. Those simulations start from tiny initial fluctuations, seed them with physics for gravity and gas, and let them run forward for billions of years. The result is a web that looks very much like what the surveys see. That match is one of the strongest pieces of evidence that our basic picture of a universe dominated by dark matter and dark energy is on the right track. You are, in effect, traveling through the outcome of those simulations. Now, bring it back to your speed. 1 light-year per second is far too slow to cross a 50 million light-year filament in under a minute in any literal way. Physically, you need more than a year to cover that length, but as a mental tool, this speed gives you a clear timescale. Each second is 1 light-year of travel and 1 year of light travel time. Each minute is 60 light-years. So if someone says, this filament is tens of millions of light-years long, you can immediately translate that to, that is hundreds of thousands to millions of minutes, or months to a couple of years of your travel. Your brain can now step through a filament in chunks. A minute per 60 light-years, an hour per 3,600 light-years, and so on, until the whole thing is covered. You are using your impossible engine as a ruler to keep these absurd numbers tied to human-sized times. So now you've scaled from clusters to superclusters, from dense knots to long filaments and huge voids, over distances of tens and hundreds of millions of light-years. You are seeing the skeleton of the universe, the layout that dark matter and gravity build over almost 14 billion years. But everything you have done so far treats distance as if it were the main quantity that matters. Beyond a few billion light-years, that breaks down. Because the universe is expanding, the distance to a galaxy now is not the same as the distance its light had to cross to reach you. And the redshift you measure is telling you how far back in time you are looking, not just how far out in space. So your next step is tougher. What happens when you start thinking of your speed not just as miles per second or light years per second, but as a direct dial on look-back time, where every extra billion light years on your odometer means you are sampling the universe a billion years younger? How far can you push this idea of 1 light year per second before distance itself stops behaving the way your intuition expects? That break happens once you get out to a few billion light years, where simple how far away is it right now and how long has its light been traveling no longer match in a clean way. Up close, distance is straightforward. If something is 10 light years away, its light has been traveling for about 10 years, and the distance it was at when the light left is not very different from the distance it's at now. But on scales of billions of light years, the universe has expanded a lot during the time that light was in flight, so you end up with 2 different distances. One is the light travel distance, basically how long the photon has been moving converted into light years. The other is the proper distance now, how far away that galaxy is right now if you could somehow freeze the expansion and measure the separation at this instant. Because space has stretched, the proper distance is larger than the naive light travel distance. So your odometer at 1 light year per second might say, I've gone 10 billion light years, but the galaxy that sent that light could now be 20 or 30 billion light years in proper distance. The simple one-to-one link between distance and look-back time starts to bend. So how do you keep track of where in time you really are when you look out that far? This is where Redshift becomes your main tool. Redshift is how much the light from a galaxy has been stretched on its way to you. The more space has expanded while the photon was traveling, the more its wavelength gets stretched, and the bigger its redshift. That stretch is directly tied to how far back in time you are sampling. Higher redshift means earlier universe, younger galaxies, denser cosmic environment. So instead of just saying, this is 10 billion light years away, cosmologists usually say this has redshift 2, or redshift 6, or redshift 10, because that number maps more cleanly to a specific look-back time and a specific expansion factor than a simple distance does. What does it actually mean when you hear that the light from a galaxy has been traveling for 5, 10, or 12 billion years? Think about it in terms of your speed. 5 billion years of light travel means the photon has been on the road for 5 billion years. On your clock, moving at 1 light year per second, that's 5 billion seconds, on the order of 160 years. 10 billion years of light travel is about 300 plus years on your clock. 12 or 13 billion years of light travel, the sort of ages we talk about for very distant galaxies, are a few hundred years of your motion. So in a lifetime or two of your travel, you can move through all the look-back times from the fairly recent universe, where galaxies are mature disks and ellipticals, out to the era where galaxies are young, clumpy, and just building up. Each extra billion years of light travel time is just another 30-something years for you, but it's a huge change in what the universe looks like. How do you read that change in the light itself? One obvious sign is how the spectrum gets distorted. As the universe expands, every wavelength gets stretched. Blue light shifts toward red, red shifts into infrared, and so on. Spectral lines that come from specific atomic transitions slide to longer and longer wavelengths. One key feature is the Lyman alpha line of hydrogen, which in the lab sits in the ultraviolet. In high redshift galaxies, this line can be shifted into visible or infrared wavelengths. Even more important is the Lyman alpha break, a sharp drop in a galaxy's brightness at wavelengths shorter than that line, caused by hydrogen gas absorbing the more energetic photons. As redshift rises, that break moves to longer and longer observed wavelengths. Telescopes hunt for galaxies by looking for objects that are bright in red or infrared filters, but drop out of bluer ones, a sign that the Lyman alpha break has been shifted into that band. That's how we catch galaxies whose light left them when the universe was only a few 100 million years old. All of this only works if you trust your distance and expansion model, and that is where standard candles and standard rulers come in. Type 1a supernovae are standard candles because their intrinsic brightness is very similar from event to event. By comparing how bright they appear to how bright they should be, you get distances to their host galaxies over billions of light years. Baryon acoustic oscillations, BAO, are standard rulers, a preferred scale imprinted in the clustering of galaxies by sound waves in the early universe. By seeing how large that feature appears at different redshifts, you can infer how fast the universe has expanded over time. Put supernovae, BAO, and other indicators together, and you build a curve for the expansion history. That curve lets you translate an observed redshift into a look-back time and a proper distance now, with cross-checks built in. You are not just guessing how old the light is, you are anchoring it with multiple independent methods. Now, fold your impossible speed into this. At 1 light year per second, each extra billion light years you cover along your path corresponds, roughly, to an extra billion years of light travel time. The match is not exact because of the expansion, but it is close enough for your brain to latch onto. When you say, I have moved another billion light years out, you can also say, I am now looking at galaxies whose light has been traveling an extra billion years. On your own clock, that extra billion years of photon flight is about 30 plus years. So a 30-year stretch of your journey corresponds to a billion years of cosmic history. A few hundred years on your clock spans most of the time from the peak of galaxy formation back to the era when the first generation of large galaxies were assembling. That is the real shift in this part of the trip. You're no longer treating your speed as fast travel across static scenery. You are treating it as a direct dial on look-back time. Every big chunk on your odometer is not just more distance, it's a younger universe. Different types of galaxies, different star formation rates, different gas conditions. So the natural next step is to push that dial as far back as current telescopes can see, into the time when galaxies were brand new, small, and surprisingly bright. The era where the James Webb Space Telescope is finding record-breaking objects that seem to grow too fast, too early. If each extra few tens of billions of light years on your counter takes you back to those first few 100 million years after the Big Bang, what exactly do you find there? And why are those early galaxies already forcing us to rethink how fast structure can form? How early in time can you actually go if you keep pushing your 1 light year per second speed into the deepest data we have about the young universe? Right now, the limit is basically set by one machine, the James Webb Space Telescope, and by a handful of galaxies it has pulled out of the darkness. Webb's job is simple to state. It's built to see the first few 100 million years after the Big Bang. It works in infrared because the expansion of the universe has stretched the light from those early objects far out of the visible range. It takes ultra-deep images with cameras like NIR-CAM, then takes spectra with instruments like NIR-SPEC, so we can measure just how far that light has been stretched and how long it has been traveling. One of Webb's core science goals is exactly this: to find and study the first generations of galaxies that formed when the universe was a few percent of its current age. Right now, two of the most extreme examples are JADE's GSZ14-0 and MO-MZ14. JADE's GSZ14-0 has a measured redshift of about 14.3. In our standard cosmology, that means we see it as it was less than about 300 million years after the Big Bang, when the universe was roughly 2% of its current age, and its light has been traveling for around 13.4 billion years. MO-MZ14 goes even farther. It sits at redshift about 14.44 and is seen only 280 million years after the Big Bang, with a light travel distance of about 13.5 billion light years. At the time you're thinking about this, MO-MZ14 is the most distant confirmed galaxy on record, and JADE's GSZ14-0 is right behind it. Now, look at their physical size and brightness. JADE's GSZ14-0 has a size of order 1,000 to a couple of thousand light years across, based on how its light is distributed on the sky. MO-MZ14 is even compact, only 240 light years wide. These are tiny compared to the Milky Way's 100,000 light-year disk, but for such small systems, they are extremely luminous and massive, with stellar masses up around 100 million solar masses or more, and intense rates of star formation. MO-MZ14 has a mass comparable to the Small Magellanic Cloud, but it has reached that state in under 300 million years of cosmic time. These are not gentle, slow-growing baby galaxies. They are already energetic, crowded environments. That's where the tension comes in. Before Webb, the standard expectation was that in the first few 100 million years, galaxies would be in much earlier stages, smaller and less massive, with star formation history still building up. WAST surveys now show a population of very bright, surprisingly massive galaxies at redshifts above 10, 12, even 14. Simulations can make some of these objects, but they are rare, and pushing to these extreme redshifts and masses strains the models. Either star formation in the early universe is more efficient than we thought, or feedback from young stars and black holes behaves differently than expected. Or, in the most radical suggestions, some piece of the underlying cosmology might need adjustment. Most cosmologists are not ready to throw out the basic model, but they are being forced to update how fast structure can assemble when conditions are right. Now, tie this back to your speed. The co-moving distance today to a galaxy at redshift around 13 is on the order of 30 to 34 billion light years. At 1 light year per second, that's around 30 to 34 billion seconds of travel. In human terms, that's on the order of 1,000 years on your clock. So to reach distances corresponding to these epochs, you would need to run your impossible engine for a few tens of billions of seconds, centuries of your time. Meanwhile, the photons from those galaxies have been on the move for over 13 billion years. Your shortcut turns a journey that takes light almost the entire age of the universe into trips that still span multiple human lifetimes. That gives you a clear sense of how deep into time these objects really sit. But none of this matters unless you know that the redshift values are real, and that's where spectroscopy comes in. Webb's NIR-SPEC instrument spreads the light from these galaxies into a spectrum, a rainbow of wavelengths. In that spectrum, you look for specific features. The Lyman alpha line of hydrogen in the rest frame sits in the ultraviolet. In JADE's GSZ14-0 and MO-MZ14, that line and related breaks in the spectrum are shifted into the infrared. By measuring exactly where the break in brightness occurs and where emission lines for hydrogen, oxygen, and other elements land, teams can assign a precise redshift. For Jade's GSZ 140, that's around 14.3, confirmed by hydrogen and oxygen lines. For MZ14, repeated NIR spec observations lock in its redshift near 14.44. These are not rough potrometric guesses from colors, they are spectroscopic measurements tied to well-understood atomic transitions. Those line measurements do more than give you a distance and an age. They tell you about the environment. The presence of oxygen lines in Jade's GSZ 140 shows that at least one generation of massive stars has already lived and died there, enriching the gas. Z14 shows signs of vigorous star formation and possible unusual abundance patterns, hinting at very rapid enrichment and maybe exotic early stellar populations. This means that by the time the universe is only a couple 100 million years old, you already have complex chemical and dynamical histories in some regions. So step back and summarize what your speed really buys you here. 1 light year per second turns the 13 plus billion years of photon flight from these galaxies into on the order of 400 years of your travel to reach their light travel distances, and about 1,000 years to reach their current co-moving distances. The increment is simple in your units. An extra billion light years is an extra billion seconds, about 30 plus years. And that extra 30 years for you corresponds to another billion years back in cosmic history. Each chunk on your odometer maps directly to a major change in how galaxies look and behave. You have now run your mental engine all the way back to the first few 100 million years after the Big Bang, to galaxies that should barely exist yet and are already forcing revisions to our early universe playbook. The obvious next step is to ask how far this can go, because even these record breakers are still well inside a larger limit. There is an outer edge to what any telescope can ever see, set not by technology but by the finite age of the universe and the way space has expanded. If you can cross the distances tied to these earliest known galaxies in centuries of your time, what happens when you keep going until you hit the real boundary, the roughly 46.5 billion light-year radius of the observable universe itself? How far out does everything you could ever see actually go if you keep pushing your 1 light-year per second speed until you hit the real wall? Right now, that line sits at about 46.5 billion light-years away from Earth in every direction. That number is the radius of the observable universe today, not its age. It means that if you could somehow pause cosmic expansion right now and lay a giant ruler from us out to the furthest places whose light is just reaching us, that ruler would read roughly 46.5 billion light-years. Double it, and the observable universe is a sphere about 93 billion light-years across. That is the region of space that has ever had time to send us any kind of light or signal since the Big Bang. So why is that radius bigger than 13.8 billion years if the universe is only about 13.8 billion years old? The key is that while light has been traveling, space itself has been stretching. When the light we see today left very distant regions, those regions were much closer. During the billions of years that photon was in transit, the universe expanded, and the proper distance to its source grew. The light travel time might be, say, 13 billion years, but the place it came from is now tens of billions of light years away. That difference between how long the light has flown and how far away the source is now is exactly why the observable radius is so much larger than the age of the universe expressed in light years. This brings you to the idea of the particle horizon. When cosmologists say observable universe, they do not mean everything we will ever see in practice with real telescopes. They mean everything that in principle could have sent us a light signal since the start of cosmic time. The particle horizon is that boundary. Anything inside it has had enough time, given the finite speed of light and the expansion history, to send at least one photon that could reach us today. Anything outside it has not. There hasn't been enough time since the Big Bang for a signal to cross that gap, even if that signal started right at the beginning. That outer shell is not a material wall. It's a limit set by causality and the finite age of the universe. Cosmic expansion is what makes this horizon a moving target. Think about a photon leaving a distant region early on. At first, the universe is smaller and the distance to us is modest. As the photon travels, space expands, and the distance it still has to cover stretches under its feet. In some phases, like when dark energy dominates, that stretching accelerates. The photon keeps moving at light speed locally, but the overall gap can grow at the same time. Whether the photon finally makes it to us depends on the full expansion history, how fast the universe grew at each era. That's why you need a real cosmological model to turn a redshift into a look-back time and a proper distance now. The 46.5 billion light-year radius is the current answer you get when you feed the best data into that model. So what does this look like in terms of your speed? At 1 light-year per second, crossing from the nearby universe to horizon distances is not a small step. A billion light-years is a billion seconds, roughly 32 years on your clock. 10 billion light-years is about 320 years. 46.5 billion light-years is about 46.5 billion seconds, which comes out to almost 1.5 trillion seconds, or around 1,400 to 1,500 years of continuous travel. That's the time it would take you, with your impossible engine, to move from here out to the current co-moving radius of the observable universe in one direction. Meanwhile, the photons filling our telescopes from those distances have been in flight for almost the entire age of the universe. And there's a subtle catch. As you head outward at 1 light-year per second, the horizon itself is also evolving. The particle horizon's radius grows with time, because every extra year that passes gives light from slightly more distant regions just enough time to reach us. But the increase is slow compared to your speed. On human scales, you can treat the current 46.5 billion light-year radius as a hard boundary for what light starting in the past can reach us now. You can go beyond it physically in this thought experiment, but any region that lies outside that horizon, right now, has never been in causal contact with us. No signal from there has ever influenced anything here. This is the part that doesn't care how good your technology gets. You can build bigger mirrors, more sensitive detectors, satellites on the far side of the solar system. It doesn't matter. The observable universe is not limited by hardware. It's limited by the basic rules. Light has a finite speed, the universe has a finite age, and space has been expanding the entire time. That combination guarantees a hard cutoff. There's a sphere beyond which you will never see. Not because objects are too faint, but because they've never had the chance to send you anything at all. So now look at what you have done. You used an unphysical speed to make the scales feel less abstract. You still ended up with this. Even if you can cross 46 billion light-years in roughly 1,500 years of your own time, there is a horizon you cannot see beyond because no light from there has ever arrived. And that is not even the deepest limit. The farthest light we do see is not from galaxies at all. It is from a time when the universe was a hot plasma and no neutral atoms existed yet. That light forms a nearly perfect background, the cosmic microwave background, and it comes from a spherical surface at almost the same radius as your horizon. If you can reach the edge of the observable in 1,500 years of your impossible travel, what happens when you hit that surface itself, where the universe switches from being transparent to opaque, and you are staring not at galaxies, but at the afterglow of the Big Bang? How far back can light actually show you? If you keep cranking your 1 light-year per second speed toward the beginning of time, there is a hard stop, and it is not at the Big Bang. It is at a wall of light called the cosmic microwave background. The CMB is not some vague glow. It is very specific. It is light released when the universe was about 380,000 years old. Before that, the universe was a hot, dense plasma of protons, electrons, and photons all smashed together. Photons could not travel far without bouncing off a free electron, so space was opaque. As the universe expanded and cooled, protons and electrons combined into neutral hydrogen. Once most of the electrons were locked up in atoms, photons could finally move freely without constant scattering. That moment is called recombination, and the light released then has been traveling ever since. By the time it reaches you, it has been stretched into microwaves by the expansion of the universe, but it still carries a snapshot of what conditions were like at that early time. In today's terms, the co-moving distance to the surface where that light last scattered, the CMB surface, is also around 46 billion light-years away, basically the same radius as your observable universe. That is not a coincidence. The CMB is the oldest light you can see, so it comes from just inside the particle horizon. It defines a sphere around us, a shell in every direction, at roughly that 46 billion light-year distance. At 1 light-year per second, reaching the radius corresponding to that surface is a trip of about 46 billion seconds, on the order of 1,500 years on your clock. The photons you are catching there have been in flight for about 13.8 billion years. So here's the key block. Why can't you just fly past the CMB and look at even earlier times with light? The problem is not distance, it is physics. Before recombination, the universe was opaque to photons. Any light produced then was scattered over and over by free electrons long before it could travel in a straight line. There is no way for a photon from, say, 100,000 years after the Big Bang to make it all the way to you without being scrambled. The last time it scattered and finally got free is around that 380,000-year mark. That is the surface you see as a CMB. Going physically beyond that radius in this thought experiment does not let you see earlier times directly, because no older photons have survived in a straight, unbroken path. You're not blocked by distance, you're blocked by the fact that the medium itself was opaque. If earlier photons are off the table, what can you use to learn about epochs before the CMB? You switch to other messengers and to theory anchored by later evidence. One is the cosmic neutrino background. Neutrinos interact far more weakly than photons, so they decouple from matter much earlier, when the universe is just seconds old. In principle, they carry a snapshot of conditions at that time. In practice, their energies today are so low and their interactions so weak that we have only indirect evidence for that background so far. Another tool is primordial gravitational waves, ripples in space-time produced by very early processes, possibly during inflation. Those waves would travel almost unhindered and could leave signatures in the polarization pattern of the CMB, or in future direct detectors. On top of that, we have Big Bang nucleosynthesis, which uses the observed abundances of light elements like helium and deuterium to pin down what temperatures and densities had to be in the first few minutes. So even though you cannot see earlier times with photons, you can still probe them through relic particles, gravitational signals, and the imprint they leave on later observables. You also have the detailed structure of the CMB itself as a probe of those earlier conditions. The CMB is not perfectly smooth. Its temperature varies by about 1 part in 100,000 across the sky. Those tiny hot and cold spots are the fingerprints of small density differences in the early universe. Regions that were slightly denser gravitationally pulled in more matter over time and grew into galaxies and clusters. Missions like WMAP and Planck have mapped these temperature fluctuations over the whole sky with high precision. They don't just give a random pattern, they show acoustic peaks, regular features in the power spectrum that come from sound waves oscillating in the hot plasma before recombination. The positions and heights of those peaks tell you about the total amount of matter, the amount of normal matter versus dark matter, the curvature of space, and the relative contributions of radiation and dark energy. In other words, the tiny ripples in the CMB map directly to the seeds of all the large-scale structure you've been flying through. From your point of view, this is a bit unnerving. You've given yourself an absurd speed. You can cross a galaxy in a day, a cluster in weeks, the cosmic web in years, and the whole observable radius in 1,500 years. But no matter how fast you travel, you cannot see past that CMB surface with light. The limit is not your engine, it is causality, plus the interaction history of photons with matter. What lies behind the CMB in time is only accessible indirectly through neutrinos, gravitational waves, and the way those early processes shape the expansion and the initial density fluctuations. So stack it up. Your impossible ship can reach the co-moving distance of the CMB in well under 2,000 years of your onboard time. The photons from that surface took almost the entire age of the universe to arrive. Anything earlier than that is, for light, blocked by an opaque plasma, and for you, blocked by the fact that no photons from that time are left to collect. There is a real horizon of causality in this problem. Inside it, signals have had time to move, structures have had time to grow, and you can, in principle, get information. Outside it, or earlier than certain epochs, you hit a hard limit, not just on travel, but on knowledge that can be carried by light. And this is where the next complication comes in. Even inside that horizon, the expansion of the universe does something more aggressive. On large enough scales, space itself moves galaxies away from you faster than light. Dark energy drives that accelerated expansion, and it creates another boundary, an event horizon, beyond which light emitted now will never reach you, no matter how long you wait. If your speed is already cheating relativity just to make scales manageable, what happens when you set that against a universe where parts of space are pulling away at effective speeds greater than light, and where an event horizon defines regions you will never be able to interact with at all, even in principle? How does your impossible speed look when you set it against expansion itself, where motion is not galaxies flying through space, but space stretching between them? Start with the basic rule. Hubble expansion says that on large scales, the recessional speed of a galaxy is roughly proportional to its distance. Double the distance, you roughly double the recessional velocity. Nearby, that just looks like everything moving gently apart. Farther out, the same rule means very distant galaxies are receding extremely fast. The important detail is that this is not them firing rockets through space. It's the metric of space itself changing with time. If recession speed grows with distance, there's a threshold where that recessional speed reaches the speed of light and then keeps going. For far enough objects, space between you and them is stretching so fast that in our usual language, they recede faster than light. This doesn't break relativity because nothing is locally moving through space faster than light, and there's no single global speed limit on how fast the distance between two faraway points in an expanding universe can grow. The limit applies to local motion through space-time, not to the rate at which the coordinate distance in an expanding metric changes. Dark energy is what makes this even more severe. Right now, dark energy accounts for about 68% of the total energy content of the universe, dwarfing both normal matter and dark matter. Its effect is to drive accelerated expansion. In the early universe, matter dominated, and expansion was slowing down due to gravity. As the universe expanded and matter thinned out, dark energy came to dominate, and the expansion rate started to accelerate. That means, on the largest scales, the distances between unbound structures are not just growing, they're growing at an ever faster pace. This gives you two important horizons, and they are not the same. The particle horizon, which you already met, is the boundary of what can have affected us up to now, the edge of the observable universe. The event horizon is different. It is the boundary of what can ever affect us in the future. In a universe with dark energy like a cosmological constant, there is a finite distance such that light emitted today from beyond that distance will never reach us, no matter how long we wait. Current estimates put that cosmological event horizon at around 16 billion light-years or so in proper distance. Anything that is right now farther away than that and not moving toward us with a strong peculiar velocity is effectively cut off forever. Its future light cones do not intersect our world line. So where does your 1 light-year per second speed fit into that? You might think you can just outrun this effect by moving fast enough. The catch is, the event horizon is not about your ship. It is about what regions stay causally connected as a universe evolves. Even if you can, in this thought experiment, cover a light year in a second, light itself still defines what information can travel where. Regions that are beyond the event horizon at a given cosmic time are those from which light emitted now will never reach us, because the expansion in between grows too quickly. You can physically move towards such a region in your own coordinates, but you cannot make light they emit today magically arrive here if the cosmological model says it never will. Your speed does not change the global structure of space-time. It only changes your path through it. Another way to see this is to compare timescales. At 1 light year per second, you could, in principle, traverse 16 billion light years in about 16 billion seconds, roughly 500 years. But during those 500 years, the event horizon itself moves, and the geometry of space-time keeps evolving under the influence of dark energy. You do not get to impose your own static backdrop. The region that is causally connected to here and now is set by the full expansion history, not by the capabilities of any ship. You can choose where you go, but you cannot choose which distant events can ever send a signal that arrives here after now. The really unsettling part is that dark energy might not even be perfectly constant. In the standard lambda CDM model, it is treated as a cosmological constant, the same everywhere, unchanging in time. But early DESI results and follow-up analyses have reported hints that dark energy strength may have evolved over the last several billion years, appearing slightly weaker at late times than a pure constant would suggest. These results are still labeled as hints, not final proof, and cosmologists are being cautious. But if they hold up, it would mean the effective equation of state of dark energy is not exactly -1, and that the acceleration history is more complicated than a simple vacuum energy. That would have huge implications, not just for the fate of the universe, but for your horizons, both particle and event. Because the exact way those horizons evolved depends on how dark energy behaves over time. So put it together. You have handed yourself a speed that erases almost every human idea of distance. You can cross galaxies in hours, clusters in weeks, the observable radius in on the order of 1,000 years. It feels like nothing should be out of reach. But the structure of space-time, set by expansion and by dark energy, still imposes hard boundaries. There are regions whose past light can never reach us, set by the particle horizon, and regions whose future light will never reach us, set by the event horizon. No engine changes that. Your impossible motion only exposes how strong those limits are. Which leaves one last question hanging over everything you've just done. If you can cross the solar system in seconds, the galaxy in a day, the local group in weeks, and the observable universe in a handful of your own centuries, but still run into absolute limits on what you can ever see or influence, what does that really say about our place in this structure, and about how tiny our home is inside it? You can, in this setup, cross the observable universe in something like a couple thousand of your years. So why does everything you've seen still make you feel smaller, not bigger? Start with the raw size ladder. The region we call the solar system, even if you're generous and include the distant Oort cloud, is maybe a couple light years across, a few trillion miles, a few trillion kilometers. The Milky Way's disk is about 100,000 light years wide. Virgo, a proper rich cluster, is a few million light years across. The Laniakea supercluster, the larger basin of attraction that includes Virgo and the local group, runs to hundreds of millions of light years. So your entire home system, everything from the sun out past the comets, is smaller than a pixel on the scale of the galaxy. And the galaxy is a tiny dot on the scale of Virgo, and Virgo is a small patch inside Laniakea. You started this journey obsessed with planets, but by the time you hit supercluster scales, the solar system is just part of the fine print. Meanwhile, the local group itself is not standing still. Dynamically, it's falling toward the general region of Virgo and the broader Laniakea environment. The Milky Way, Andromeda, and their dwarf galaxies all share a bulk motion, a few hundred miles per second, hundreds of kilometers per second, relative to the smooth Hubble expansion. That motion is driven by the combined gravity of Virgo and other massive structures nearby. You're riding on a galaxy that's slowly sliding downhill into a deeper gravitational well, while energy tries to stretch space apart. Over billions of years, that flow helps feed matter into larger clusters and superclusters. But on your 1 light year per second scale, you blow past the space those flows will gradually traverse, long before the galaxies themselves ever get there. Then there's the long-term fate of those galaxies. On small scales, the future is mergers. The Milky Way and Andromeda are on track to collide and merge in several billion years. Inside clusters like Virgo, galaxies fall in, lose gas to ram pressure stripping, and get shredded or absorbed by bigger members. On large scales, the universal star formation rate has already peaked and is declining. Gas gets locked up in stars, then returned in less useful forms or blown out of galaxies entirely. Over trillions of years, star formation shuts down. Galaxies turn red and faint as only long-lived, low-mass stars remain. In a universe with dark energy, gravitationally bound systems like the local group or Virgo stay together, but everything not tightly bound gets carried away by expansion. You end up with isolated island universes, lonely clusters or groups surrounded by a vast, empty, unreachable dark. New observatories keep forcing us to redraw the map on every one of these scales. The Vera Rubin Observatory will deliver deep, repeated imaging of the entire southern sky, catching faint dwarf galaxies, tidal streams, and subtle lensing patterns that reveal dark matter around and between galaxies. It will show you more of the Milky Way's substructure, more satellite galaxies in the local group, and more detail in nearby clusters. JWST is pushing the high redshift frontier, finding surprisingly bright, compact galaxies in the first few 100 million years, and exposing how fast structure can grow when conditions are right. The Nancy Grace Roman Space Telescope will map huge volumes with sharp infrared imaging and spectroscopy, tightening constraints on dark energy through supernovae and galaxy clustering. Each time a new facility comes online, the cosmic map gets updated. Things you thought were rare turn out to be common. Structures you thought were simple turn out to be layered and messy. Even so, crossing the observable universe in a few thousand of your years would not show you everything, and not just because there's too much to list. You are limited by horizons. You cannot see earlier than the surface of the cosmic microwave background with light, because before that, the universe was opaque. You cannot get information from outside the particle horizon because light has not had time to get here from those regions. You cannot get future information from beyond the event horizon because light emitted there today will never reach you, no matter how long you wait. Flying faster does not change those facts because they are baked into space-time itself, not into your engine. There is another subtle limit. Every time you look out, you are not seeing the universe now. You are seeing a slice of its past light cone. The more distant an object is, the younger it appears. If you travel to some distant cluster and look around locally, you see that region at its current age, not at the young stage you saw from home. There's no way to watch the same object at all stages of its life at once. You always see either its past from far away or its present from up close. Even if you run this trip for thousands of your years, you are still only sampling one thread through spacetime, one history experienced from one world line. The full four-dimensional story is bigger than anything a single observer can ever record. So what does this journey actually give you, beyond a parade of big numbers? It forces a reset on your sense of scale. The solar system, which feels huge because it dwarfs everything in daily life, collapses into a flicker, gone in under a second. The Milky Way, which sounds unthinkably large at 100,000 light-years, becomes a day-long crossing. The local group, a miniature cluster of galaxies, fits into weeks. Virgo and the surrounding web fall into the span of years. The entire observable radius, 46+ billion light-years, can be crossed in roughly 1,500 years on your clock, but is still bounded by horizons you cannot break. You also see that the universe is not just big, it's structured and time-dependent in a very specific way. Small-scale structures live inside larger ones, from stars to galaxies to clusters to superclusters and filaments. All of them grew out of tiny density ripples seen in the CMB. Their growth rate depends on the mix of normal matter, and dark energy. Star formation rises, peaks, and declines. Mergers build up big galaxies from smaller ones. Dark energy takes over and freezes structures into isolated islands. None of this is static. Every distance you cross has a history and a future attached to it. Thinking in light years per second strips away the comforting illusion that these numbers are just abstract labels. It ties each distance directly to a time: 1 year of photon flight per second of your motion, 1 billion years of cosmic history per few decades on your clock. It makes you confront the fact that even an absurd speed leaves you trapped inside one finite observable region, with strict limits on what you can influence or even know. You started by asking what you would see if you traveled at 1 light year per second across the cosmos. The answer is, you would see that the solar system is nothing, the galaxy is small, the clusters are local, the web is finite, and the universe is ruled by horizons and time. And the most unsettling part is this: you do not need a real ship to feel that. You just need to let these scales sink in and accept that on every level, from a fraction of a second in the solar system to thousands of years across the observable universe, you are living in something far more extreme, structured, and temporary than your everyday experience ever suggests. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.